Okay, so in front of us is an RTX 3080 Ti that unfortunately is not detected when inserted into a working system. So in order to confirm that it's not detected, we're going to be using a Vega 64 as a primary display device, and then we're going to boot into the Windows, scroll to Device Manager, and confirm that it's not in the list of display devices, so we can verify that the 3080 Ti is actually non-functional. Anyways, let's go ahead and do that. And let's turn off the light. Okay, so first things first, let's go to Device Manager and confirm the 3080 Ti is not detected. So under Display Adapters, you notice how we have the Vega, let me zoom in, but there is no 3080 Ti. And if we check GPU-Z, we have the Vega, which is what you're looking at right now, but on the drop-down menu, there is no 3080 Ti. Let's go to an overhead view so I can show you why it's non-functional. Okay, so as many of you can already tell by the title, this is a backwards inserted mining riser card, meaning that the problem with this card is the fact that it has a fried PCIe lane at the first pin on the first pair. If we check in diode mode using our multimeter, we get 2.7 volts. If we check the second pin in the first pair, we get 1.8. And if we check a random lane, we get, again, 1.8, which is consistent with all the other lanes as well. Yep, 1.8. Anyways, so we have a fried differential pair at the first PCIe express lane. The part that you probably didn't realize is that the Vega that you saw running a game is also a backwards inserted mining riser card. If we check the first pin at the first lane, we get 0.6, second pin at the first lane, 2.8, and a random lane, 0.8. Meaning that this actually has 2 damaged pins at the first PCI Express lane. Yet, as all of you already saw, this card can run a game at full load without issues. Oh, and one more thing. For those who can't tell, this card has been baked before, as you can kind of see. So if I had to guess, I would say the first owner inserted a riser backwards, and then sold it to someone on eBay who then baked it, who then sold it again on eBay to somebody who sent it in for repair, where that third owner finally abandoned the card and now it's here. Anyways, let's go ahead and continue with the rest of the video. So, how is it that this card can work, but our 3080 Ti doesn't? And much more importantly, how do we get our 3080 Ti to run, given that it is the much more valuable and expensive card? Well, in order to do that, let me first explain something about backwards inserted mining riser cards and why more than 95% of them are basically dead forever. So, to do that, we're going to use yet another card, a 3060 Ti. So this is a backwards inserted mining riser card. And typically what happens when you insert the riser portion backwards into your motherboard, it sends 3.3 volts down that first PCI Express lane. Generally speaking, like I said earlier, this pretty much always fries the core, and it basically always fries the PCIe lane, but in most situations, like 95% plus, it also fries the reference clock pins at the back of the card. For example, on this one, if we check reference clock plus, which is the second pin after the notch, we get a short, and if we check reference clock minus, which is the third pin after the notch, we get an open line. So this thing, not savable. But, unlike this 3060 Ti, our 3080 Ti actually seems kind of hopeful. If we check the reference clock plus, 0.85, and then check reference clock minus, again, 0.85, which is what it should be. Now, I should note that just because the reference clock pins are not shorted does not mean the card can be saved or made to work again, or I should say made to run again. There are other things you need to check, like the PEX rail, 1.8 volts is common, and even if they all check out fine, the card could actually just be dead and not show any obvious symptoms. So the rule is, if there's something wrong with the reference clock pins, and it's due to a mining riser, the card is dead forever. But if the reference clock pins are fine, the card may be alive and, in a sense, salvageable. Which, of course, brings us to the next concern. How does one get a 3080 Ti like this to run again? After all, it is an expensive card, it is very fast, and it would be a shame if this thing was headed off to landfill, given how much money it costs. Well, thankfully for you, I have a couple of ideas. Let's first go over the standard method employed by most working technicians. Okay, so you've inserted your card backwards into a mining riser, and I should say the mining riser backwards. What do? Well, like I said, let's go over the standard method. So first you need to confirm it's a candidate for PCIe remapping. I already went over this slightly, and I'm not going to go over it again. Anyways, so the standard method is as follows. Basically, the idea behind the standard method is that we're going to take our damaged PCIe lane at the first lane, and we're going to rewire it to another lane that is still perfectly functional. So the standard method is that if you have an NVIDIA card, you will rewire lane 1 to lane 2. So on the front side, and the backside, involving 4 wires total. And if you have an AMD card, you will rewire lane 1 to lane 16. Front side and backside, no biggie, right? And the standard method, despite its crudeness, actually has a few merits. So the first merit being that it actually gets you a working card, which is great if the card was not detected before, which is most backwards inserted mining riser cards, even if they are, in a sense, salvageable. And it allows you to use the card at most of its potential, but not all of it, as we will later see. So the second merit is the fact that it is perfect for reuse in a mining rig. If you are the kind of awful, evil person that wants to take a backwards inserted mining riser card and then insert it into yet another mining riser for your mining rig, this method only consumes 1 lane of bandwidth, allowing you to reserve the rest of your bandwidth for your other small army of presumably backwards inserted mining riser cards. Now, the best part of the standard method, in my opinion, is the fact that you don't actually have to modify the cards yourself. Instead, you can just rewire the riser, as one of my Discord members has done in the picture below, and he used this to get his 3080 running in what I presume is another mining rig. I could be wrong, maybe he used it personally, but like I said, it lets you modify the riser itself and not the PCB, as you'll later understand is, in my opinion, a pretty heavy benefit. So for all the merits that the standard method has, it does have a few notable drawbacks. The first and main one, in my opinion, is the fact that it's an X1 rewiring, so that you're unfortunately going to suffer a rather hefty performance decrease if you try to use it, let's say, outside of mining. So if you're running games, for 2080 Ti, going from X16 to X4 2.0 gives you a 21% decrease. So this is 2.0, not 3.0. So where X4 2.0 has the same bandwidth X2 3.0, which has the same bandwidth as X1 4.0, which is what a 3080 Ti can use at best using the standard method. So like I said, for 3080 Ti, I would guesstimate that the performance decrease would be around 30%, roughly speaking, with some outliers being 50%. And if you have a 50% performance decrease, you're looking at roughly 1080 Ti performance, in which case you may as well sell your 3080 Ti and just get a 2070 Super or whatever. So the next problem with the standard method is that apparently it cannot be extended beyond 1 lane. So this was true a year ago, and double checking with some of the Germans that I know who have very large graphics card repair communities, they don't know any method of extending it beyond 1 lane. So for the purpose of this video, we will say that 1 lane is the best you can do, and even if you could extend it to say 8 lanes, rewiring 1 lane requires 4 wires, which means that presumably if you could use 8 whole lanes, you'd need 32 wires across 64 traces, which itself is a lot of work and kind of messy, and generally not something we want to do given how time inefficient it is. Which also then leads us to the next problem. Assuming you could actually rewire 8 whole lanes, would you have the required signal integrity to actually run the card? So it's generally well known that PCIe 4.0 risers are notoriously unreliable. They don't have copper insulation required to run PCIe 4.0, and even some motherboards can't actually do PCIe 4.0 despite advertising as such. For example, this Z690 RTX board, the Aeos Ultra by Gigabyte. That board is famous for having to have a PCIe 3.0 version because Gigabyte got the PCIe 4.0 signal integrity wrong and caused stability issues for a lot of owners. If you were to say extend the standard method to 8 lanes, assuming it was doable, and you rewired 32 wires across 64 traces, if one of those wires was, let's say, not up to spec or didn't have enough insulation, do you trust that you'd be able to find exactly which wire it was in a timely fashion? I'm going to say probably not. Which of course leads us to the method that we will actually use in this video. But in order to use that method, you need to understand 2 features. Okay, so the first method you need to be aware of is this thing called forced bifurcation. You'll understand later why we call it forced. So basically, the idea is that instead of, let's say, using all 16 lanes of your graphics card, instead, we'll break this up into 2 smaller bits of 8 lanes and only use the last 8 lanes. So in particular, we want to be using this one on the right side. So we don't want this, but we do want this end. So I should note that, generally speaking, the reason why we call it forced bifurcation is because by default, your motherboard is designed to run whatever X16 device you have in X16 mode. Instead, what we will want to do in some very niche cases is break this X16 into, say, X8. Generally speaking, you won't ever have to do this, but you do need to be aware of it, because in some cases, you will have cards that are intermittently stable, as in they can sometimes be made to work using that first PCIe lane, but they can't always. Like, for example, the Vega that you saw running a game will, let's say 1 out of 10 times, crash on driver install or crash when the drivers load. In general, for a card like that, even though you could get away with running it in X16, it would be a lot cleaner just to cut off the first 8 lanes and restrict ourselves to the last 8 lanes. And in fact, a lot of AM3 Plus motherboards already do this. For example, if you have an AM3 motherboard, AM3 Plus motherboard with a 970 North bridge, it will use the last 8 lanes instead of all 16. When the first lane is fried, that is. And the card will be detected and work. Despite being a rather neat feature of AM3 Plus motherboards, it forces you to use an AM3 Plus CPU. So because force bifurcation is generally kind of limited, that brings us to the next method. And that method is lane reversal. This method in particular, or maybe I should say feature, is the real star of this video, because this is what makes using a backward inserted mining riser card possible on basically any modern Intel system. So the idea is of course very simple. Instead of, let's say, having the first physical lane be the first lane electrically speaking, instead what we're going to do is we're going to make the last physical lane the first lane. And then we're going to make the second last lane the second lane, and the third last lane the third lane. And we're going to go backwards from there. So typically speaking, what this will do is that it will force your card to run in X8, because your motherboard will detect that there's an issue with the first lane. And of course, X8 is great, because as I think you should have, yes, that's right. As you have seen from previous graphs, and as you can guess, running your card in X8 only results in like a 1% performance loss, typically speaking. So if you have a 3080 Ti, running it in X8 gives you basically the performance that you'd expect from a 3080 Ti, minus of course 1%, which is margin of error. And better than this, not only can you run the last 8 lanes, but if you choose to run multiple devices in your motherboard, like multiple PCIe cards, where typically the last 8 lanes get sent to the lower slots, then you'll still have a working graphics card, because you'll be able to run the last 4 lanes of the first 8. So these 4. So this would be 1, 2, and so forth until you get X4, whilst ignoring the first 4. And then even better than this, if for some reason you have to insert it into an X4 slot, you'll get to use these 2 lanes. So this one becomes 1 and this becomes 2, giving you X2 functionality. Anyways, let's go to an overhead view. Okay, so lane reversal and force bifurcation sound great and all, but how do we actually apply this to a graphics card, and what do we need to do so? Well, let's start with what we don't need. We don't need a hot air station. We don't need a soldering iron. We don't need the graphics card in question, and better than all of this, you don't even need a technician like yours truly. No, all you need is a piece of aluminum tape, aluminum by the way, not aluminum, and access to your processor. Let me explain. Okay, let's go over force bifurcation and lane reversal. So these features are not actually features of motherboards. They used to be features of motherboards when they had North bridges, but today your modern Intel processor and semi-modern Intel processor can actually activate these features using a set of resistors on the board itself. So basically, there's a couple of pins under your processor that connect to a resistor, which may or may not connect to the ground. If it says 1, it's not connected to ground. If it says 0, it is connected to ground. So the trick, in order to, let's say, activate bifurcation or lane reversal, is simply to bridge one of those pins to ground. Like you can install a resistor, but as you kind of were shown, or at least hinted at in the previous clip, you can also take a piece of aluminum tape and then bridge, let's say, the lane reversal pin, which is this one here, to ground, where the ground pin is diagonal from the lane reversal pin. I use aluminum tape because it's conductive, but you can use whatever you want. And like I said earlier, this is not restricted to Alder Lake. For example, we can go to, let's see, here we go. There should be a lane mapping table. There we go. So here we go. So this is for 8th and 9th gen CPUs. And as you can see, they also use the same configuration resistors. Unlike Alder Lake, Skylake and its derivatives actually do use configuration 6, because they can split from 1x8 into 2x8 to 1x8 plus 2x4 instead of just 2x8 like Alder Lake does, since Alder Lake has a dedicated M.2 lane. Anyways, let me show you what pin this is on an Alder Lake CPU as well as a 9th gen CPU. Okay, so first things first, if you're looking at the underside of your Alder Lake CPU, the arrow needs to be on the bottom right over here. Now, assuming you have that done, the pin that you need to bridge to ground is as follows. I apologize for the low quality image. So you're going to start with the bottom right corner here. You're going to start with this pin, one below the bottom right corner. Then you're going to go 1, 2, 3, 4, 5. And this pin is the lane reversal pin, where this is ground and this is ground. If you need to know where the bifurcation pin is, it is this one here, and this is ground, and this is ground. Hopefully that makes it easy. Okay, let's suppose you have a Skylake CPU or one of its derivatives. First things first, the arrow needs to be in the bottom right, once again, and then you start at this weird pin over here, the circle. So then you go 1, 2, 3. 1, 2, 3, 4, 5. And that is your lane reversal pin, where this is ground, this is ground, this is ground, and this is ground. Okay, suppose you now want to bifurcate from X16 to X8, X8. Starting at your lane reversal pin, you go 1 up, 1 left, 2 left. And now you have your configuration resistor to split from X16 to X8, X8, where this is ground and this is also ground. Now let's say you want to split your last 8 lanes into X4, X4, so you get X8, X4, X4 total. Starting from your X8, X8 pin, you go 1, 2, 3 up, 1 across. And this is configuration 6 to split your last 8 lanes into 2 X4 lanes, where this is ground and this is ground. Oh, and also I forgot to add that this is ground as well over here. That is more or less how you would do it. So like I said, all you need is a piece of aluminum tape. You short these pins to ground using a piece of aluminum tape, where the ground pins are basically right next to them, and then you can force lane reversal or bifurcation. So anyways, let me go show you what my brief attempt at it. It's not a very good attempt, but I will show you. Okay, so this is me putting tape, bridging 2 pins using tape. So this is in the Alder Lake one, bridging lane reversal to ground. I should note that for bifurcation, this can often be set in the BIOS, but as far as I can tell, lane reversal is rarely ever set in the BIOS, if ever, on consumer motherboards. It technically can be set in the BIOS, it's just not implemented. But if you have a relatively modern motherboard, you can at least set the bifurcation in the BIOS. Anyways, let's go to the testing and demonstration, and then we'll finish off the video. Okay, as you can see, the card is running in the topmost slots, and as you can also see, it's running a game. Let me turn off my lights. But anyways, if we go to GPU-Z, you'll notice that it's running at X8 3.0. 3.0 because this motherboard only supports 3.0, but it is using 8 lanes. And just to be clear, these are the last 8 lanes in reverse order. So like I said, you know, lane reversal is definitely a way you can make your graphics card usable again if you have, you know, one of these fried PCIe lanes, but perfectly good reference clock pins and perfectly good everything else as well. Anyways. Okay, so I'm going to cut the video short because its length is getting a little out of hand. It looks like it'll be more than 20 minutes, maybe, and I personally wouldn't even watch a TV show if the episodes were more than 20 minutes. Never mind some sloppily edited YouTube video. So, first things first, I have a pretty big disclaimer about lane reversal. It's optional. As in, your graphics card, your processor, your motherboard, whatever, doesn't actually have to support it. I forgot to mention it earlier in the video, and it is a major thing to consider. However, in my testing, which I recorded in a spreadsheet linked in the description, across multiple motherboards, lane reversal was supported by GTX 1070, RX 580, 2080 Ti, Arc A380, 3080 Ti, Vega 64, and RX 6800. So it seems like the vast majority of graphics cards will support it, minus a few niche cards like maybe lower end AMD cards that don't have full 16 lanes of bandwidth, and maybe reduced PCIe controllers, maybe. Anyways, speaking of AMD actually, I don't know how to activate lane reversal on an AMD processor. I want to say it is supported, I do believe it's supported, but I can't find any documentation suggesting such, and I can't find any method of activating lane reversal if you have an AMD motherboard. If you know something about it, please link it in the description. Naturally, you'll get upvoted to Oblivion, or Heaven or whatever, and everyone will be able to read it, and then I can try to test it on my one B350 RTX board, as well as my Ryzen 5 3600, given to me by the guy who gave me the Celeron that I use for testing as well. Flagship Labs, by the way, link in the description. So, as for lane reversal itself, the general rule is that without lane reversal, you'll get 0 lanes, of course, with a 3080 Ti like this, but if you have lane reversal, you should get half of these lanes available in that slot. If you're running your, let's say, 3080 Ti in an X16 slot, and electrically X16 by the way, then you get 8 lanes. In an X8 slot, you get 4 lanes. In an X4 slot, you'll get 2 lanes. And if I had an X2 slot to test, if they even exist, you should get 1 lane in theory, though I haven't tested it. As for bifurcation, generally speaking, force bifurcation, you won't really have to activate this. most motherboards will work fine, and most graphics cards will work fine with the auto setting. But in the off chance that you have something like the Vega, which is intermittently faulty, you may want to cut off the last 8 lanes and just run on the first 8 lanes. And by first 8 lanes, I mean the physically last 8 lanes, but then the first 8 electrical lanes when using lane reversal. So just something to keep in mind. Otherwise, I think that's it actually. So to me, the beauty of this method is not that it gives you 8 lanes of bandwidth, and by extension 99% performance for your 3080 Ti or whatever. To me, the beauty of this method is that you don't need a hot air station or a soldering iron, and better yet, you don't even need a technician. If you have a piece of tape, and you have access to your processor, and you have 20 minutes of time and a bit of knowledge, you too can restore your 3080 Ti, getting 0% performance because it's not detected to 99%, which I think is great, given that this card would have otherwise ended up in a landfill, along with many others. Anyways, like I mentioned earlier, I have a spreadsheet detailing the test configurations I ran across 3 motherboards in the description if you want to read it. I also have a Discord server if you want to talk to me about it, but please don't try to bug me over things that are obvious. Anyways, thank you for watching. I hope you learned something, and hopefully I will see you all in the next one.